Good day, everybody. So welcome to week 2 of your mechanics course. So what we're going to do today is continue with same ideas of what we learned last week. Specifically, we're going to still consider momentum, conservation of momentum, and what we're going to do today is finish off with some rotational considerations, which will lead us into week 3. So just a quick recap. Remember last week we were talking about impulse, and impulse is force times time. More specifically, we were able to do something very general, is actually take a look at the force as a function of time. And we also saw that impulse is a difference in momentum. So you have your final velocity and your initial velocity, and what we did is we looked at it at that. So impulse is a change in momentum, and so what we're going to do today is first off, we're going to start off with conservation of momentum, and we're going to consider collisions. Now we're going to go into much more detail. There's a whole chapter on collisions, so this is just a very brief introduction to collisions, and we're going to get into more meat and potatoes later on as we develop the course. So the very first thing we're going to consider is frontal collision between two particles with masses m1 and m2. So here what we have is mass m1. So this is its momentum before collision, and this is its momentum after collision. So we got the little subscript 1. So particle 1 and initial and final. Now there's going to be a lot of subscripts that show up. So just to bear in mind what we're going to see later on in the course, we're going to define momentum, initial momentum, as u1. So that will be initial velocity. However, for now, we're just going to stick with that notation because we're actually not going to go too far with this idea just now. So again, just to bear in mind that we're going to see this again later on, and instead of having all these scripts all over the place, we're actually just going to label initial velocity with u instead of v. So we have before collision, after collision, and then so what we have is the impulse for particle 1. And likewise, we could take a look at the exact same stuff for mass 2. So before collision, here's its momentum. After collision, here's its momentum. And so the impulse between for mass 2 is final collision, final momentum minus initial momentum. And so once again, we use all the definitions that we have for impulse. So impulse is a change in momentum, but it's also equal to a force and an applied time. So what does this mean is why is conservation of momentum so important, or why do we even have conservation of momentum? Well, it's according to Newton's third law. So Newton's third law, as we all know, it's the one that everybody seems to remember, is for every action there's an equal and opposite reaction. So what this means is that during a collision, so again this is mass 1, and this is for mass 2. So you have two particles that enter in collision, and so according to Newton's third law is force F1 is equal to minus F2, and so we know what that is. So what we're going to do is they're obviously in contact with each other for the same amount of time, so we multiply each side with delta t, and so that then just implies that the impulse felt by mass 1 is equal to the impulse felt by mass 2, but of opposite direction. And so what is the impulse of mass 1? Well, it's as we stated, so there's the final momentum minus the initial momentum, and same thing for mass 2, there's the final momentum minus the initial momentum. So ideally what we'd like to do, let's just reorganize these. So we put all the initial on one side, all the final on the other side. So here we have initial conditions. And so over on this side, we have final conditions. So this is conservation of momentum. So the initial momentum of our system is equal to the final momentum of the system. And this is true for all cases. So it doesn't matter what type of collision you have. So what you're going to see is in some of the simulations that you have, it could be an elastic collision or a plastic collision or even an explosion. You always have the condition that the initial momentum is equal to the final momentum. So let us take a look at a quick little example. So again, ideally, if you did this example ahead of time, or if you haven't, again, I would recommend just pause the video just for 2 seconds and give this problem a try. So what we have here is a 200 kilogram cannon fires a 5 kilogram cannonball with a speed of 500 meters per second. So calculate the recoil of the cannon. So obviously this is the exact same idea as what we have say for any gun or anything like that. Every time you fire it, those of you who've went hunting, fired a shotgun or a rifle or anything like that, you'll notice that there's a recoil, and so it has to be nicely lodged in your shoulder so you don't actually hurt yourself. So how you would go about tackling these problems, and again, this is the way that I do it, you're free to solve it any which way that you like, is I like to start off with calculating the initial momentum. And you'll notice here that I'm very general. I'm saying the initial momentum of the system. So it doesn't necessarily just have to be 2 particles. It could be 3, it could be 4, it could be a million particles. So the entire system, momentum of the system is conserved. So we have m1 v1 initial plus m2 v2 initial. And so this is equal to, we'll say 1 is the cannon, and we'll say 2 is the ball. And so we're assuming that everything's at rest. So you got the cannon, we haven't fired anything yet. So the initial momentum is equal to 0. Then we want to find out, well, okay, so what's the final momentum? And again, of the system. Let's be completely general. Doesn't necessarily only have to be 2 particles. So we got, oops. So what we have is m1 v1 final plus m2 v2 final. And so what information do we know? Well, again, so m1 is the mass of the cannon. So how much is the cannon? How much does the cannon weigh? It's 200 kilograms. And what we're trying to do is find out what the recoil of the cannon is. So basically what we're trying to find out is what is the final velocity of the cannon. And then we got the mass of the cannonball, which is 5 kilograms, and it leaves the cannon with a velocity of 500 meters per second. And so this is the final momentum of the system. And sure enough, then we can apply the law of conservation of momentum. And basically what this said is 0 is equal to 200 v1f plus the momentum of the cannonball. And so this then will just simply allow us to solve for the final velocity. You'll notice the negative sign. Again, momentum is a vector, so this is direction. So if the cannonball shoots off in that direction, the cannon goes off in that direction. And then we plug in our numbers and we get 12.5 meters per second. And again, this is the recoil. Good. So hopefully that wasn't too bad. And so that's where we're going to stop for momentum considerations. So what we did so far, again, remember in week 1, we had impulse, we talked about momentum, we looked at different momentum considerations, we looked at it applying a certain impulse, we looked at the relationship between force and time and velocities and momentums. And so here what we did is we just took it one step further, we finished it off that little section, and we looked at conservation of momentum. Now we're going to completely switch gears, we're going to look at something completely different, and we're going to start taking a look at rotational considerations. What you're going to see is all going to tie up very, very nicely at the end of this chapter. So we're going to start off with rotation, and then honestly, we're going to finish off with conservation of angular momentum. So we finished off linear considerations with conservation of momentum, and we're going to finish off at the end of week 4, I believe it is, with conservation of angular momentum, or it might be next week. So rotation, so as we're all very familiar with rotation, we're not going to spend too much time with this one here. So again, angular displacement, so here's the rotational body. So you have a particle up here, travels on a circular path down to part B, and so it goes some certain distance, which is some angle. There's different ways that we can measure that angle. So if you separate a circle into 360 equal divisions, that's 1 degree. So obviously there's not 90 divisions here, but that's 1 degree there. Again, I don't think we're saying anything new here. We can also define the unit in terms of radians. And so if this is the radius of our circle, if the distance that it travels is exactly 1 radius, that is by definition, this angle here is 1 rad. Again, I don't think it's anything new. And obviously what we do is we convert between the two very, very often. However you want to convert it is up to you. Again, I'm not going to ask you to convert it a specific way. I personally just remember this. So 2 pi is the entire circle, and an entire circle is 360 degrees. So this is the conversion between the two. But again, if you want to remember this or if you want to remember that, that's completely up to you. I just always use 2 pi is equal to 360. And again, well, I think, again, we all know this. Pi is equal to 3.141, goes on to infinity. So very, very quick examples just to remind ourselves. Let's convert the following angles into rads. Again, you may have done this already, and I'm sure that you're very, very apt at being able to do this. So 50 degrees. So 50 degrees, again, however you want to do it. So 50 pi rad divided by 180 degrees is equal to 0.873 rad. We have 135 degrees here. I'm just going to give you the answers. Again, I'm more than confident that everybody's here able to do it. Is 2.36 rad, and obviously 360 degrees is equal to 2 pi. So there's the rotational displacement. What we could also look at is arc length. So again, arc length, remember if we have our circle, and however you want to, you could imagine a mass or a race car, or however you want, is traveling around this circle. And so this is what we define as the arc length. And so what is the arc length? So the arc length, we're going to give it the symbol S. And the arc length then is the radius of the circle. So there's the radius. And times the angle, the angular displacement. And the angular displacement, very, very important, has to be given in rads. So you'll notice then that the arc length is simply the angular length times the radius of the circle. And we're going to see this relationship over and over and over again. So if you want the linear component, it's basically the angular component multiplied by the radius of the circle. You're going to see it over and over again. So for a quick example, given an arc length of 3 meters, calculate the angular displacement in rads and degrees if the radius is 5 meters. So very quick, S is equal to R theta. And so we want to find out what is the displacement then if it travels 5 meters along the circle. Or sorry, it travels 3 meters. The radius is 5 meters. And so that's 0.6 rad. And in this case here, it asks to have it in degrees as well. So that's 34.4 degrees. Good. We can also express the angular displacement in terms of revolutions. We won't really use revolutions for in terms of angular displacement. We tend to use it a lot more for velocity. We're going to see that in a few minutes. Velocity, I'm sure everybody's familiar with an engine is turning at such RPM. Again, RPM is revolutions per minute. So what is one revolution? Well, one revolution is exactly that. It does an entire revolution around the circle. So again, there's a circle. If this is our starting point, well, we go right around. That's one revolution. So again, by definition, one revolution is 360 degrees, which is equal to 2 pi. So we could do this again. So 34.4, this is the conversion. So 34.4, how many revolutions is it? Oh, it's 0.0956 revolutions. So that's angular length or arc length. Then we also have angular velocity. So angular velocity is given by the notation omega. So it's not W. Looks like a W, but it's an omega. And as always, remember that velocity, linear velocity, is equal to position divided by time. So again, the exact same thing. Angular velocity is the position, the arc length divided by time. If position is not a function of time, then you could just derive it. So you got delta omega over delta t. So there's your angular velocity. And as mentioned a few seconds ago, several problems that we're going to do is we're going to express everything in revolutions in a frequency. So frequency is revolutions per second, but most likely what we're going to have is revolutions per minute, as in this little example that we have here. So what is the angular velocity of a disk if it has a frequency of 30 revolutions per minute, or again 30 RPM? So in most problems, in order to get numerical answers, what you have to do is you have to express everything in radians per second. So radians for displacement, radians per second for velocity, and radians per second square when we're going to talk about acceleration in a moment. But obviously all these units can be in different quantities. So in this case here, what we have is revolutions per minute. So what we have to do is we have to convert. So we have an angular velocity of 30 revolutions per minute. So again, however you want to do this. So 1 minute has 60 seconds. And a revolution has 2 pi rad. And all this then comes out to 3.14 rads per second. And so that's your actual angular velocity in rads per second. So there's angular velocity. Again, we have angular acceleration. Again, I don't think we're giving anything new here. So angular acceleration in this case here is given the symbol alpha. And similar to the linear consideration, we have acceleration is equal to dv dt. So same thing, angular acceleration is equal to d omega over dt. And again, so it's just a change in angular velocity over a change in time, or omega f minus omega I over change in time. And so now that we have all three considerations, we have position, velocity, and acceleration, what we could do is we could combine all three. So if we start from the very basic with acceleration, so we have this is by definition. If acceleration is not a function of time, then what we could do is we could separate it. We could put the dt over here. We integrate on both sides, and there, lo and behold, in general, we have the condition that t initial is equal to 0. So now we have acceleration is equal to that. So basically, I just derived this equation up here. So what we could do is we could take it one step further. So what we do is we start off with angular velocity is the time derivative of position. But now what we have is the angular velocity, remember, coming up here. So we're going to bring that down here. And so now what we have is the angular velocity is equal to alpha, the angular acceleration times time, plus its initial angular velocity. And so what we do is we now take this and plug it into here. And then we take the time dt over onto this side, integrate both sides. Again, you'll notice that I set t initial is equal to 0. And so now what we have to do is we integrate alpha t. So that's alpha t squared. That's where we get the 1/2 plus omega I t, the initial velocity. And that's equal to the final position minus the initial position. And so therefore we get this nice equation, which again we're very, very familiar with in terms of linear. So this is angular displacement. But we're all very familiar with the linear component. So remember, linearly what we have is the final position is equal to 1/2 the acceleration t squared plus the initial velocity t plus the initial position. So if you remember, we're all very familiar with that equation. So again, exactly the same thing for angular, except just different symbols. So as an example, then let's take a look at what we have here. We have the angular velocity of a wheel passes from 6 to 12 revolutions per second in 8 seconds. What is the angular acceleration in rads per second squared? So again, hopefully you've already tried this problem. If you haven't, again, just stop the video for a few seconds, give it a shot, and then tune back in. So what we have then, we're looking for the acceleration. Acceleration is final velocity minus initial velocity divided by time. So the final velocity is 12 revolutions per second. We could convert that into 24 pi rads per second. The initial velocity is 6 revolutions per second, which is 12 pi rads per second. And so now that will allow us then to calculate what the angular acceleration is. And this acceleration took place in 8 seconds. So again, this is assuming that we have a constant acceleration. Needless to say, if you know me by now, we're probably going to be looking at an acceleration as a function of time. But for now, let's keep it simple. So obviously your answer is acceptable, 1.5 rad. Or if you take 1.5 times pi, 4.71 rad per second square. And so therefore you have your final acceleration, or the acceleration for that particular problem. So similarly, we have a couple more problems. In this case here, very similar, except now we are given the acceleration. We have a grinding wheel having an acceleration, an angular velocity of 6 rads per second, receives a constant acceleration of 2 rads per second squared, and we're asked what is its angular displacement after 3 seconds. So again, we're asked for the displacement, final displacement. So we're assuming constant, well, we're not assuming, it said constant acceleration. So if we have a constant acceleration, we're free to use this equation. We're going to assume that at time t is equal to 0, the position is equal to 0. So the acceleration is 2. Time, we've accelerated it for 3 seconds. Its initial velocity was 6. And so we get 27 rad. So if we have a grinding wheel with an initial velocity of 6 rads per second, and we give it a constant acceleration of 2 rads per second squared, after 3 seconds it will have gone through 27 rads. And here's where we get a little bit more interesting. What is its angular displacement if the angular acceleration is no longer constant but given by the following equation? So again, we always assume that the angular acceleration is a constant, But in this particular case here, what we have is it's a function of time. So we have a constant factor here, but we also have one bit that varies with respect to time. So in that case, we have to go back to our initial definition. So what is the acceleration? Well, it's d omega over dt. So therefore we have back our differential equation. And basically what we have to do, again, it's not very complicated. All we have to do is plug all our numbers in. And again, I reiterate, this is not a math course, so Miss Rice is going to be teaching you differential equations and math in 232. So we're going to keep things relatively simple over here. So what we have is, so the integral of a dt is just at. The integral of bt dt is plus bt squared over 2, and that is equal to omega. And if we just rewrite this a little bit, so now what we have is the final velocity is equal to this equation. So if you remember, this is exactly what we had before, except we didn't have this term in it. So this is a new term. So we're asked, what is the final position? If we were asked what the final velocity was, well, we don't have to go any further, but we were asked what the final position is. So again, we go back to our definition of angular velocity. It's d theta over dt. And so what is our velocity? Well, it's now given by this equation. And so what we have to do is we integrate all that. So this d theta is just delta theta is equal to, so what's the integral of at? Well, it's at squared over 2. What's the integral of bt squared over 2? What's bt to the cube? And then we have 2 times 3, so that'll be 6. And omega I dt is just nothing other than omega it. And so if we assume that the initial position was equal to 0, so that's when we started our clock, then we could say, well, then the final rotational displacement is equal to at squared over 2 plus bt cubed over 6 plus omega I t. And then we could plug in the values. What is the value of A? It's 2. The value of B was 1. And the initial velocity was 6. And so after 3 seconds, the final position cancel these off. So it will have gone through 31.5 rads. And so that's it for this week. Hopefully you didn't find that overly challenging. So there's a lot of final little assessments to be done before you could attempt the problem set, or perhaps you've already done the problem set, in which case hopefully there wasn't too many difficulties. And that's it for now. So next week what we're going to do is we're going to continue again with these ideas. We're going to introduce the concept of torque, and we're going to introduce the concept of angular momentum, and then we're going to finish off this section which will then lead us into a completely new topic, which is collisions, which will then revisit what we've seen last week and a little bit at the beginning of today. So I hope that wasn't too bad, and I hope you guys have a great week. Stay safe, and we'll talk again next week. Take care. Bye.